Hey, this is AP Calculus Lecture 5.9A. In class, I give this lecture all as one, but on video, I'm going to divide it into two just to make shorter videos. The lecture is about inverse trig integration. Really, it just involves pattern recognition, and you want to have your inverse trig formula sheet, and we'll only be using these three formulas, at least for our new material. We might go back to the derivative formulas as well, and also, of course, use some of the things that you've learned in the past. All right, so let's just go straight into the example problem. So our first one is example 2 on page 390. You'll want to have your unit circle handy as well, because we will be doing some, I need to get mine, we will be doing some plug-in derivatives here, some definite integrals. All right, so example number 2, we're going to integrate from 0 to 1 of dx over the square root of 4 minus x squared. So what pattern does this look like? Well, it's got a square root in the bottom, and it looks like arc sine. It doesn't have the u out front like arc secant does. So the first thing to figure out is which one is it, and this one is arc sine. So looking at the formula, you're got to pick out what is u and what is a. All right, what is u, what is a? Well, a always goes with the constant, and a is going to be 2 in this case. Okay, so the square root of 4 is 2. U would be x. All right, since we have x squared and u squared's in the formula, so now we just go straight back to the formula. It's the arc sine of u over a. Okay, so we have the arc sine of x over 2, and we're going to integrate that from 0 to 1. So plugging in, we would have arc sine of 1/2 minus arc sine of 0. Well, the angle whose sine is 1/2, all right, remember sine comes second on the unit circle, that's pi over 6. And the angle whose sine is 0 is 0, so the answer is pi over 6. All right, so one down and several more to go. All right, let's look at number 4 on page 390. And that one we are integrating from root 3 to 3 of 1 over 9 plus x squared. So if you'll look at your formula sheet, you'll see that the pattern that this matches is arctangent. No square root in the bottom. A, of course, a is your constant. A would be the square root of 9, which is 3. And then u is going to be the square root of x squared. Okay, so the formula is u squared, so u would be x. So if you'll look back at your sheet, of course, we know this is arctangent. So the formula is 1 over a, so 1/3 arctangent u over a, so x over 3. And since this is a definite integral, we have to plug in our limits. So this would be 1/3 arctangent 3 over 3, that's just 1, right? Minus 1/3 arctangent root 3 over 3. Okay, the angle whose tangent is 1, that's pi over 4. So we'll have 1/3 times pi over 4 minus 1/3 the angle whose tangent is √3/3. Okay, so you can remember this. If it's just √3, it's pi over 3. If it's √3/3, it is pi over 6. If you want, you can go through the tangent is equal to sine over cosine and work that out, but it's easier just to memorize that. So we're going to have pi over 12 minus pi over 18. Okay, if we change this to a denominator of 36, that's 3 pi over 36 minus 2 pi over 36. Multiply this by 3 over 3, pi over 18 by 2 over 2, and that'll give you just pi over 36. All right. Let's take a look at number 6. All right, we want to integrate 1 over 4 plus x minus 1 all squared. Okay, so there's no radical in the bottom. You've got an a squared and a u squared. So this is arctangent. A is going to be 2 square root of 4, and then u will be just x minus 1. So the formula, and we don't have a definite integral here, so we can just put plus c at the end. So this is going to be 1/2 arctangent u over a, x minus 1 over 2. Going to put parentheses around that to show that that is the angle, or that is what you're taking the arctangent of that entire quantity, not the angle, excuse me. All right, plus c. All right, just plug and chug on that one. Okay, let's get into a couple of examples that are a little more of a pain. We still have our pattern recognition, but anytime that u prime or du does not equal 1, we have to go through u substitution. So using u substitution with inverse trig integration. We must use anytime du does not equal 1. Okay, in the previous 3 examples, when you took the derivative of u, you got 1. It's not going to be the case in a couple of these upcoming examples. So let's look at example 10. And we want to integrate t over t to the 4th plus 16. Now there's no radical in the bottom. We look like we have a u squared and an a squared here. So u is going to be the square root of t to the 4th, so t squared. A is the square root of 16, which is 4. So du will be 2t dt. I want du to be t dt, so let's divide both sides by 2. 1/2 du is equal to t dt. So we can rewrite this integral in terms of, all right, in terms of u. So we would have du over u squared, so t to the 4th. If u is t squared, then u squared would be t to the 4th, plus, and then that would be a squared, so 4 squared. So we know that's arctangent, okay, because of the recognizing the pattern there. And so let's plug into the formula. So it would be 1/2 out front. We have this 1/2 times 1 over a, so 1 over 4 arc tangent. Okay, it's going to be u over a, so I'll just go ahead and put u over 4 plus c. So that's 1/8 arc tangent. U is t squared, so t squared over 4 plus c. So if you forget to do the u substitution there, your fraction out front is going to be wrong. And that is not a minor mistake. All right, so be very careful on the test and on your homework doing these. Make sure you check to see if du is equal to 1. All right, let's do a couple more examples. All right, our next one comes from number 18 in the book. We're integrating 1 over 3 plus x minus 2 all squared. Now still, this one looks like arctangent. Okay, no radical in the bottom. U is pretty simple. It's just x minus 2. Okay, it's not squared. A looks a little different. Don't let this freak you out that 3 is not a perfect square. A is just going to be the square root of 3. If you square the square root of 3, you get 3. So the answer would be 1 over a, 1 over the square root of 3, arctangent x minus 2 over the square root of 3 plus c. So this one didn't involve u substitution because the derivative of u, du, is 1. But I wanted to give you an example like this to show you that your a doesn't have to be a perfect square. Okay, let's do one more example in this video. And this one doesn't come from the book, so we're going to integrate dx over x times the square root of 4x squared minus 9. So looking at your integrals, the one that this looks like is arcsecant because you have that x out front. All right, looks like arcsecant. So if we try to figure out u and a, u would be the square root of 4x squared. Well, that's 2x. A would be the square root of 9, which is 3. Well, this one we're going to have to do a u substitution. So du is 2 dx. It's not 1. So 1/2 du is equal to dx. So let's rewrite this in terms of u. All right, so we've got a 1/2 out front. Okay, we have a dx on top, so now that's just going to be du. Now this x, if u is 2x, then x would be 1/2 of u. So we're writing this in terms of u. So half of u, and then I would have u squared minus 3 squared. All right, so that's going to be the 1/2 out front. But look at that. I don't even have to put that. That 1/2 cancels out with the 1/2 on bottom. Okay, so I'm just going to lightly mark through that. Okay, the 1/2 cancels out. And so now we can look at our pattern on our sheet. We got 1 over a, so 1/3. And arcsecant, the absolute value of u over 3 over a, right, plus c. So finally that's 1/3 arcsecant absolute value of 2x over 3 plus c. Okay, so we were fortuitous this time because the half out front and the half canceled. That might not always be the case. And that's going to do it for this video. I've got a couple of more examples coming up. We'll call that video 5.9b, and I will talk to you then.